experiment, you are going to measure the magnetic field of the Earth. You're going to do so using this Hall probe. In addition, you're also going to measure the magnetic field inside a solenoid, or in your case, the solenoid is actually a Slinky coil. In this first part of the experiment, you are going to determine the magnitude and direction of the Earth's magnetic field by finding the maxima of the magnetic field registered by the Hall probe in two directions. We can first rotate the probe and see in real time that the direction and magnitude of the field changes. We can see this change in the registered magnitude graphically by clicking the green arrow on the screen. If we turn the probe in a full circle, then we see a cyclic behaviour of the registered magnetic field strength. The Hall probe which you use in this experiment has an associated zero error. What this means is that even if there was a zero value for the magnetic field around you, i.e. no magnetic field, it would still not measure a zero value. If you wish to measure the magnetic field strength in a certain direction, first take the measurement in that direction, then rotate the probe through 180 degrees and take a second measurement. We will call this first measurement B1 and we'll call the second one B2. We now have two measurements of the magnetic field strength. First, we're going to call B1. The second, we're going to call B2. We're going to look at another quantity which is the zero error of the device, which we will call delta E. Okay. Because we measured B1 and B2 in opposite directions, then we have to look at what these quantities actually stand for. Let's call B the true value of the magnetic field. Therefore, B1 is composed like so. A measurement in the opposite direction to get B2 looks like so. So the question is, with these two quantities, how can we eliminate this error here? Well, the answer is simple. We just subtract B1 and B2. If we do that, then we see we get twice the value of B, which is the real field measurement, and we eliminate the zero error. So we in fact end up with 2B. Hence, if we divide this quantity by 2, then we get the real value for the magnetic field. Having found the direction of this maxima, we then want to measure along the components of the magnetic field. Firstly, we're going to measure a horizontal component. We measure first in one direction, and then we measure its pair in the opposite direction. Second of all, we want to measure the vertical component, which corresponds to this orange vector here. We first measure a vertical component in one direction, and then reverse the probe and measure the vertical component in the opposite direction. What we then have, once we have taken these two measurements, is we have vertical and horizontal components of the resultant magnetic field vector. And hence we have an indirect way, by measuring the vertical and horizontal components, of measuring the actual magnetic field vector. By Pythagoras' theorem, we can now measure the value of the magnitude of the magnetic field strength, having measured its components. can see where the maxima is from this graph. The maxima are the peaks of this plot. So that for this second part of the experiment, you'll need to line the probe up in the direction that corresponds to this maxima here. The connection of the Hall probe and the lab probe to the computer follows as such. First, take the plug for the Hall probe and connect it to channel 1 on the lab probe. Next, take the USB cable. For the more square end, connect this to the opposite side of the lab probe. Then take the rectangular end of the USB cable and connect it to the USB port on the computer. The power cable then connects into the base of the lab probe, where it is clearly labelled by the power supply symbol. Next, turn the power on at the source. The tone that comes from the lab probe tells you that the device is ready for use. For this third part of the experiment, you will need a number of different pieces of apparatus. You'll need the power supply, alligator clips, an assortment of different numbers of cables, the Slinky Coil, a mass, a multimeter, and a rheostat or variable resistor, in addition to a switch. Note that it is the push button type. Firstly, take the Slinky Coil. Loop one end over the heavy weight. This serves the purpose of securing the Slinky to one end of the bench. Next, take the other end and drop it off the edge of the bench. The Slinky should now have spacings of approximately 1 centimetre between each of the adjacent loops. This comes in handy later on in the experiment for inserting the Hall probe and taking measurements. From the positive terminal of the power supply, connect a lead, and then to the other end of the lead, the crocodile clip. The crocodile clip then attaches to one end of the Slinky like so. From the other terminal, attach another lead. Attach one end of this lead to the switch. From the switch, run the circuit to the rheostat or variable resistor. Then from the other end of the variable resistor, continue the circuit to the ammeter. From the ammeter, the circuit then connects via the crocodile clip to the other end of the Slinky. And then the power supply is turned on. To take a measurement of the magnetic field strength inside the Slinky coil, we first want to set the multimeter as an ammeter. We turn the switch so that it is in this green part of the dial. We then take the Hall probe and insert it into the coil. We take a measurement in one direction by depressing the switch. As you can see from the ammeter, a current is now running in the circuit. We then take the Hall probe and rotate it through 180 degrees. We then take another measurement at the same current. Let's go to the computer screen and see what's happening when we take such measurements. I have the Hall probe aligned in one direction. I'm then depressing the switch, and we can see we get our first reading. I now let out the switch, I rotate the probe, and I'm now taking a measurement in the opposite direction. I'm now about to depress the switch. This is then our second measurement at the same current. We now have two measurements of the magnetic field strength at one current. We are then able to subtract the two quantities, divide by 2, and this gives us a value for the magnetic field strength without the zero error. Remember always when taking a measurement to only leave the switch depressed for a very short amount of time. This is because the current flowing through this circuit heats up the Slinky coil very rapidly. We then want to repeat the measurement that we previously made for a number of different currents. We take the probe and insert it. We adjust the rheostat, depress the switch, and then take 2 readings as before. And then we repeat that process for many different currents by using the rheostat to adjust the current. For the final part of this experiment, we want to measure the magnetic field strength at several different positions along the coil. To do so, insert the probe at one position, and in the previous manner, take pairs of readings in the opposite directions. We move along the coil, inserting the probe at a number of different positions, and as you can see, we're taking measurements first in one direction and then in the opposite direction. From what you know about solenoids, try and form a hypothesis about what the field strength is at each different point along the coil. How do you think the field strength should vary as you move along the coil? From the experiment, you now have many different measurements of the magnetic field strength B versus the current I. Recall that you changed the current with the use of the rheostat. You can now plot your data points on a graph with axes B versus I. From this equation here, you would expect the relationship to be linear. That is, you would expect the magnetic field strength to be linear in I. You can plot your data points like so. And the data points that I have drawn represent what you would expect for this experiment. Having plotted your data points like so, you can then draw a line of best fit. Having drawn your line of best fit, you now have a gradient of this relationship of B versus I. If we return to this expression here, then we can realise that the gradient of this line, which we will call G, is equal to mu naught times n. Recall that mu naught is the permeability of free space, and n is the number of turns per unit length. You can measure the number of turns per unit length in your Slinky coil. Once you have this quantity, divide both sides of this equation by n. So now you have an estimate of the permeability of free space, mu naught.